Welcome to our latest tutorial on the Firetail visualization suite. I'm Tobias, machine learning scientist and software engineer at Schäuffelhut-Berger. Today I would like to introduce you to a feature that may well have quite some impact on the way that you interpret and how you annotate your data. So this tutorial will be about our machine learning assisted acceleration data segmentation, aka FireSOM. In the first part of this tutorial, I would like to give you an abstract overview of the key ideas of the FireSOM algorithm. In the second part, I will show you a practical example of how to annotate a real-world dataset. I refer to this feature as FireSOM, as the core algorithm is based on self-organizing maps, but also because the name is much shorter and sounds a lot fancier. So, let's assume you have done the hard work and now have a set of tagged animals in the wild producing data. The tags work as expected and have been recording locations and movements for several weeks. Fortunately, current tags will provide very detailed information. Interpreted in a mutual context, these sensors paint a quite complete picture of an animal's behavior, which summarizes pretty well the whole idea behind Firetail. The most commonly captured data is the animal location. It likely encodes a lot of information on high-level behavior. The tags may also provide acceleration data, orientation, altitude, temperature, or custom sensor data. It is now important to understand that to infer behavior, we would typically identify recurring patterns in our data. For spatial data, this is intuitively clear. For example, it's relatively easy to identify regions that an animal visits repeatedly. For the other sensors, unfortunately, the recorded outcomes can be extremely abstract. The visual interpretation of similarities is hard or impossible. So how to make sense of this kind of data? From a perspective of behavioral analysis, high-resolution acceleration data is very promising. It's recorded with high resolution, it can be recorded when no location is available, and it is tightly coupled with local movements of an animal. Flying birds or bats would show repetitive accelerations, while resting and foraging would result in fewer peaks or arithmetic records. In general, we expect that each activity would produce a specific recorded pattern. If for distinct activities the patterns are distinct as well, it's reasonable to assume that we can infer behavior from the data. Certainly, we may find very similar data for different activities as well. In general, two distinct activities that look the same across all recorded data cannot be discriminated. Given that it is possible, how can we infer activities from data? Manual annotation would definitely require several experts and a good amount of time. Depending on the study length, manual annotation may be completely out of scope. Plus, achieving a good level of agreement among annotators may be challenging for complex data. At this point, let me give you a short primer on the options that we have from a machine learner's perspective. In practice, most algorithms would follow two main strategies. The so-called supervised strategy will use a set of existing annotations to train a predictive model. This model is capable of distinguishing predefined categories and can then propose a class for each new fragment. Supervised approaches are very powerful, yet the training and the evaluation of these models can be tricky, as most models require careful control against overfitting. Further, you have to annotate thousands of examples in a possibly complex setting and cover all desired categories. If you like to add a behavioral category later on, this may force you to get back to the annotation bench and start over. Speaking of Firetail, a supervised algorithm that yields reliable predictions across various datasets and that can be parameterized by conservational biologists would be extremely challenging. In this context, the typical machine learner would definitely prefer to stay close to the code and avoid large-scale re-annotation. Please trust me here, I'm one of them. But let's have a look at the other option. The unsupervised strategy analyzes the inherent structure of the data. Similar patterns will get assigned to nearby regions in the model. Thus, similar bursts are placed in one cluster or are nearby in a phylogeny of burst patterns. The parameters that define unsupervised models are usually more interpretable, like the number of clusters to be predicted. A good thing about clusterings and unsupervised approaches in general is that they will assign a category to your data with virtually no previous knowledge about the nature of the dataset. That's a bit of a lie there, because in practice, the way you look at the data can make a huge difference, but that's okay for now. There is a catch, though. The predicted categories are not labeled. We do not know which category reflects flying or sleeping or whatever. We only know that the predictions reflect the structure of the data. So, how do we resolve this problem using FireSOM? At the core of FireSOM, we employ a self-organizing map. Think of it as an actual two-dimensional map, similar to old Hexfield strategy games, or simply a honeycomb. FireSOM's training algorithm will place all acceleration bursts on this map by encoding them as features. The resulting map is structured in a way that similar bursts are either neighbors or live at the same spot on the map. From this map of bursts, we derive categories that reflect the structure and similarities present in your data. Each predicted category is placed in a separate layer. As discussed before, the initial categories are not assigned to any activity. They should be interpreted in the context of all available data first. The good news is, Firetail is designed for this very task. You can view all sensor data fully synchronized, inspect locations, as well as acceleration and orientation patterns. This way, you assign categories manually, but there are some pretty striking advantages. Firstly, there is no requirement to interpret similarities and annotate thousands of bursts from scratch. Instead, you are dealing with annotated regions that are designed to be interpreted. Secondly, only a small fraction of all predictions has to be inspected to come up with a category. Verification and refinement are much faster if you know what to expect to see at crucial regions in your data. Still, machine learning is never perfect, and you should not expect initial models to match all data characteristics perfectly. In fact, we encourage you to examine FireSOM's parameters. Play with different map dimensions and start with a few burst features. Later on, increasing the number of features may increase the algorithm's power to distinguish similar patterns as well, but this may also lead to more complex predictions. A few refinement operations can help to come up with a sensible overall annotation. Sometimes, you may find that predictions are pretty similar despite being assigned to separate clusters. You can join layers using Firetail's established annotation mechanism. For example, separating different modes of flying may be irrelevant for your research question at hand, so you would simply merge them. Some prediction categories, however, cover quite heterogeneous data and are too broad. A local prediction is required. FireSOM allows you to select a range of bursts and to cluster these separately. This can be helpful to detect weak pattern deviations within seemingly uniform regions. You may even select non-consecutive regions, but let me get to the part 2 and work through an example. Okay, here we go. I started Firetail, and now I start by opening an individual ID from MoveBank, entering my credentials to log in the MoveBank server. Now I'm searching for the dataset fruit bats. This is straw-collared fruit bats in Africa, 2009 to 2014. Let's open this one. Will be downloaded. We just take the first ID here, the 1079. If you are questioned whether to accept the appropriate license, just click OK. Here we have a new feature of Firetail 7, which allows us to download only a restricted range. So in this case, we could enter a start and end date. In this case, we want the complete data set, so we take download complete data. Press OK. I downloaded this previously, but let's repeat it for now and override the appropriate files and open the individuals. Here we have the default view in Firetail that you may be familiar with. We see the event data on the right, where we can scroll in to get more details. We here see the burst data view on the top. And we see, of course, the GPS data that has been recorded. somewhere between the 26th of August and the 29th of August. So this is a pretty short recording here, but for the presentation this will do. So now we want to segment this data set, and obviously this is data for fruit bats, so we already see in the respective GPS data that there will be some points where the fruit bats will be flying, and there will be some points where the fruit bats will be resting and staying. The acceleration data unfortunately looks pretty complex, so we do not initially really know how to cluster this and how to make sense of this. So I will start by choosing the calculate ACC segmentation, which is basically our terminus for FireSOM in Firetail. We start with let's start with 12 predicted categories. That means and the underlying self-organizing map will have 12 nodes that will be used for the clustering. We do not yet want to restrict to a selection, and we want to keep the features relatively simple for now, so we use basic statistics across the X, Y, and Z axis. And start by pressing OK. So you see now make this a bit larger. So we now see that the clustering is already complete. And we can overview the annotated categories. We see the predicted categories here on top. We could add own categories, but at the moment we will stick with the predicted ones. So now let's try to make sense of this. Of course, in this case I'm not a fruit bat expert. I'm not a scientist, behavioral scientist, I'm a machine learner. But in this case, what you see pretty well is that similar patterns have been assigned similar regions above here. And in this case, you can just go here and you see, okay, we are in this region, we are definitely in a flight acceleration pattern. When we go closer, we can literally see up and down movements in the respective axis. In this case, the y-axis is green, the x-axis is red, and the z-axis is blue in here. And most of the cyclic patterns that we can observe is encoded in the z-axis in this regard. So experts can tell me then whether this is typically for flight, but my initial guess is it is flight. So I seek for the label 1-1.1, which is this one. I press a right click on it, and I type an initial guess of what this could be, or an expert decision, like this. I tell this is a new layer name, which is flight, and I give it the type A, flight, because it's like very intense acceleration at this point. So now we see a new layer with the name flight came up, and this annotation here has the type A. So what can we do now? We can look for other sections that have been labeled in the same manner, and we see that in this case an equal pattern here has been labeled with the type A as well, which is pretty convincing actually. So now we see another increased level here, which immediately follows the flight. So let's do just a guess there and say this 1 minus 2 0, so this 2 0. Let me tell you a bit about the terminology here. So in this case, we have a two-dimensional self-organizing map. And this is just the index, is index 2, 0. So row number 2, column 0. So we can just give an arbitrary name and arbitrarily name this. So let's do something like landing. And let's give this just a category like L1. Now let's see whether this landing pattern may occur after similar regions as well. In this case, you can just scroll through. I see one here, if you have a look at this. So you see that after the flight pattern, we see the L1 pattern again. So we, of course, we do not yet know whether this is actually a landing pattern, but it's definitely worth analyzing the respective region in more detail. Let's jump to the L1. And we see here that the fruit bat is currently placed within a tree, and the movements are relatively static. So it's like 1, 0, and this is the category 0, 0. So let's say this is stationary, and simply call this category as 1. And you see how this is evolving, yeah? You see that we can iteratively go through our data set, look at the speed over ground, the heading, the height that was recorded, the associated temperature, whether it's night or day, for longer observations. And what you see is we arrive at a systematic classification of all patterns in the data set. So, for example, here, when we do a replay there, we see some slight movements that are increased here. So let's replay this. And somehow at this point, there is this stationary movement again. But this is obviously more active than the stationary movement in 2,1. Into the 2-1 cluster. So let's see whether this is also stationary. Should be. We do have 2 GPS points in there. So let's see. Yeah, they're both basically on the same position. So let's call this stationary S2. And what you see, it will basically be placed to the same layer. But these are 2 distinct categories anyway, so this is what we would expect here. So I could continue to do this, but of course we do not want to annotate the complete data set now. I will reopen the data set and discard my predictions that I had for now. And let's reopen the individual 1079 from the local data. Here it is. And just reapply our FireSOM prediction here. Let's again do 4.3. Let's choose a prefix of I for the default. And only predict with the most basic statistics here. So in this case, this would boil down to the magnitudes. So now let's say that In this data it's not so much, but for some data we have additional regions that are less interesting. So maybe we are only interested in some segment of the data. Let's select this one and select another one. And we want to only predict this with a local model where we annotate this with a separate prediction. I'll make this 3 times 3 predicted categories, and let's rely on, in this case, only a very different set of fold changes. Let's just take continuity and the axis fold changes and say we want to restrict to the selection. And let's give it another name so we won't override our initial prediction. So let's do this, and what you see is the prediction we receive for the selection, the S prediction, is only seen in the respective regions that we have selected, and is only viable in these regions. And what you also see is when you go into this, then you also see a refinement here. So in this case, we saw that there is stationary movement, but with the general model, this was classified into one cluster. And with the local model, we can see into the details that, for example, there is slight movements within this bigger cluster that we did initially, the I cluster at 3, 0. But the S1, the S01 and S1 and S02 can actually distinguish these patterns and also point to regions where there's simply slight movement in this region, or basically no movement at all. And we also see that there are sub-patterns that are hardly distinguishable by the naked eye, but that our algorithm can detect and that have to be interpreted somehow. Or maybe you simply want to join them and just say, okay, 1, 2 and 1, 0 are basically the same, so let's join these and put them on the same lane. So let's do this. Let's create lane N, or maybe one of the lanes that we did before. So stationary, and we choose the name as 1 in this case. And for the S12 option, we choose the stationary and term it S2. And now we have joined them and we have categorized this as S1, and still we have this S02 category here, which obviously deviates enough from S1 and S2 to actually form a separate cluster for this local model. So, and of course, all of this data should always be interpreted in terms of the available metadata that you have. We could also jump to defined points in time where we have annotations that we can use. So, well, I hope I could give you a short introduction into what is possible with the new annotation feature. And maybe you have an idea how powerful this can be in practice, to actually interpret complete data sets and to annotate complete data sets. This feature is ongoing development, so stay tuned and have fun working and experimenting with Firetail. Thank you.